Um, all right, so this will be part 2 of chapter 5 lecture, which is basically doing the problems. We start with this traffic light example, which, actually I went over in class, but, I'm going to do it again. It's an important example where we use Newton's first law. So basically it's the application of Newton's first law. So we have a traffic light weighing 122 newtons, hangs from a cable, tied to two other cables fastened to a support. The upper cables make angles of 37° and 57° with the horizontal. These upper cables are not as strong as the vertical cable and will break if the tension in them exceeds 100 newtons. Does the traffic light remain hanging in this situation, or will one of the cables break? All right, so we are given a system which is in equilibrium, and we know that because this particular, part, right, it tells us that it hangs, which means it is in static equilibrium. So then we are given three unknowns. We don't know tension 1, we don't know tension 2, we don't know tension 3. So those are unknown, all of them. So that means we need to find each tension, so then we can figure out if the tension 1 and 2, technically those are the two important, tensions that we want to know if they will break or not. All right, so so what we do here is this. Because we have three unknowns, we have to break the system down into two parts or two systems, mini systems. Because every time you are using the Newton's first law, remember? So you get that free body diagram, force table, and an equation. Remember, you get two equations. And with equation 1, remember, you are looking at the net force in the X. With equation 2, you are looking at force in a Y. But still, you have two equations. With two equations, you can calculate up to only two unknowns. We have three unknowns. That means we cannot use directly, one system to solve for three unknowns. Right, but it's not a, let's say, it's not that difficult to take this particular example and break it down into two systems. So here's what we have. So you have tension 1, tension 2, and then this is that support point, right? So basically you can see right there that support point that connects three tensions together. And here's a traffic light, let's say. So what I'm gonna do here is I'm gonna break it down into two systems. Here's gonna be system 1. This is my system 1. And here's gonna be system 2. Okay, let me kind of make this one is a little bit. So here's my system 2. So you can see that. Because every time you break down your, let's say problem into two systems, you always want to make sure that at least one force or one something connects those two systems. In this case, you can see, right, tension 3 is in both systems. The reason we do this is because I can use then system 1 to solve for one of the unknowns, and you want to make that, let's say, your system 1, whatever is you call it, your system 1, right? You want to make it very simple. That means you have one system that you can use to calculate maybe like one unknown, and maybe it has only one unknown. And then you go back to the system 2. Now that you solved for tension 3, let's say, you go back to system 2 and you only have tension 1 and tension 2 as unknowns. So that's kind of like the rough idea. That means I'm going to take here as my system 1. I'm going to say, okay, so the system 1 is just a traffic light, and then let's say this tension 3, right? The traffic light in this case becomes my object of interest. So here's the traffic light as a particle at the center. And I'm going to then draw the free body diagram for that. It's easy because what I have here is there's a tension 3. All right, so let me make this. And then there is this, weight of the traffic light. Only those two forces. Well, if I'm doing the force table, here's the force table. X direction in a Y direction, it becomes relatively simple because I have T3 and I have weight, and those are the only forces I have, right? So you can see that none of them is in X direction. T3 is in a, I'm taking positive to be, up to be positive Y direction. So tension 3 is positive. Weight, on the other hand, negative because it's down. And I know that here, when I do put 0, this is where the net force goes, but because it's in equilibrium, net force I know for sure is 0. All right, so from here I get equation, let's call this equation 1. I'll put it like that. So this is equation 1. T3 minus weight of the traffic light equals 0, which means T3 is equal to the weight of the traffic light. And I'm given in the problem that traffic light has 122 Newton as a weight. That means I solved for the T3, 122 Newtons. So that's why system 1 is simple enough that I can easily calculate one of the unknowns. So we get 122 Newtons for the tension 3. Now, when I go back to this system 2, well, I have only two unknowns, T1, T2. I can carry this value of T3 into my system 2. All right, so let's do that then. So here's my system 2. And by the way, like for the system 2, so let's say I'm going to take this point over here as my point of interest, because that's where all three tensions, are connected. That means, tension 1, 2, 3 are exerting force at that, support point. All right. So this is my system 2 then. Taking that support point here at the center, I'm going to take up positive Y, to the right positive X, and I'm going to see that right now there are, let me kind of make this a little bit. All right. So I have then, here's one force. This is tension 1. Here's another force. This is tension 2. And then here's the third one, which is tension 3. So I have 3 forces acting on it. We are told that there's a 37 and 53 degrees. So we kind of given this. So there's a 37. Well, if that's 37, means this is 37. And we're given that this is 53. Well, if that's 53, that means this is 53. All right, so we get those from there. All right, so then that's my complete free body diagram. Step 2 will be force table. All right, so here's my T1, here's my T2, here's my T3. They're combined together is net force, but it's in equilibrium, so I get 0, 0 for horizontal net force and vertical net force. Let's look at T1. Well, T1, taking theta being with respect to negative x-axis, right, that 37 degree. So I can, remember, you can take the theta with respect to positive x-axis, which will be 180 minus 37. But in this case, I want to do in terms of like those 37 and 53 that is given, which is, remember, you can always get exactly the same thing. Becomes T1 cosine of 37 for the x component, T1 sine of 37 for the y component. The second thing that you want to look at here is the quadrant for tension 1, and it's second quadrant, which means x is negative, y is positive. Tension 2. Well, again, theta given with respect to positive x-axis makes it as T2 cosine theta, which is T2 cosine 53. for the X component and T2 sine of 53 for the Y component. T2 is first quadrant, positive, positive. T3 has no X component and acting in a negative Y direction, so you put it like that. So that's my force table. So then from here we can set up my equation. So equation one for this system is the net force in the X direction. And that will be, so basically T1, negative T1 cosine 37 plus T2 cosine of 53 equals 0. Equation 2 will be T1 sine of 37 plus T2 sine of 53 minus T3 equals 0. In the equation 1, I basically, get this, right? T2 cosine of 53, move the T1 cosine 37 to the right, becomes equals to T1 cosine of 37. Equation 1 becomes T1 sine of 37. So equation 2 becomes T1 sine of 37 plus T2 sine of 53 equals T3. Move the T3 to the right, but I have the value, so it's 122 newtons. I can just write it like that. All right, so the next step will be recognizing that you are given two equations with two unknowns. And generally, we can always solve for those two unknowns with two equations. And the easiest one to do is maybe do some kind of substitution. Going back to equation 1, you can see that I can divide both sides by cosine of 53. And then left side is T2. On the right side is T1 times cosine 37 over cosine 53. And I can do that ratio, cosine 37 over cosine 53. I end up with 1.33. That's the ratio of those cosines, 1.33 times T1. That means I can represent T2 in terms of T1. Then using that means this T2 equals 1.33 T1. Using this in equation 2, I can substitute for T2. Basically, I can replace T2 with 1.33 T1. So if I do that, I have this then T1 sine of 37 plus T2, but now instead of T2, I'm using 1.33 T1. Sine of 53 equals 122 newtons. Again, why am I doing that? Because now look at equation 2. I have only T1 as an unknown. That means I can solve that. See, I can factor out T1, becomes sine of 37 plus 1.33 sine of 53 equals 122 newtons. And all I have to do is just solve for T1. Take T1, 122 newtons divided by that, right? Sine of 37 plus 1.33 sine of 53, because those are the values that I can easily calculate. And if I do, I get 73.4 newtons. That's the value of my T1. So I already had T3. I just calculated T1, then take this and move it to equation 1. We can then solve for T2, which is 1.33 times T1, which we solved to be 73.4 newtons. That equals to 97.4 newtons. That means our tensions, our T1 equals 73.4 newtons. T2 is equals to 97.4 newtons. And T3 was equals to 122 newtons. Those are our three unknown tensions. And remember, the question was, will the tensions break? Because T1, T2 could not handle anything greater than 100 newtons. And we can see T1 and T2, both of them are under 100 newtons. That means we are safe, and then the traffic light will not fall. Cables will be able to, hold them. All right, so in this example, we're gonna look at application of Newton's second law. So we have person weighs a fish of mass m on a spring scale attached to the ceiling of an elevator. All right, so in this example, what we have basically an object that will be changing what we call apparent weight in the elevator, depending on if elevator is accelerating, basically speeding up or slowing down, or if it's at rest. So let's start with case one, which is elevator with no acceleration. That means acceleration is 0. Now, for example, if here's the fish, what you have here is this. This is the weight on the fish, and this is the tension. And let's say the reading of the scale based on the value of the tension. That means it gives you the value of the tension. Now, if acceleration is 0, then, so this is simple enough that I can just do this, right? So then tension minus weight equals, remember, this is my net force, equals, mass times acceleration. But since acceleration is 0, tension minus weight equals 0. Means tension is equals to weight. That means when you look at the reading of the scale, you read the tension. But since the weight and tension are the same, then you can say that the reading is directly your value of the weight. That's basically what you do also when you stand on a bathroom scale. What the reading does is shows the, sort of like a normal force. But since you are at rest relative, your system is at rest, right? Your room is not accelerating. Bathroom scale, the normal force and weight are equal to one another, and you get your weight because the normal force equals to your weight. Okay, so how about case 2 when you have the elevator accelerating? That means here's what I have. So the elevator is moving up. So elevator starts moving upward, but there's also an acceleration upward. That means as you move up, there's also up acceleration. And if you have velocity and acceleration in the same direction, you get then increase in velocity, remember. So that means it's a positive acceleration. Well, what we get here is this. Again, if this is the fish, here's the weight, and here's the tension. Well, now if I do tension minus weight, that's my net force, right, in the y direction, equals mass times acceleration, let's say vertical acceleration. Well, my acceleration is no longer 0. That means this m times ay, that term is no longer 0 because I do have a positive acceleration since acceleration is upward. But in this case, tension equals then, if you move the weight to the right, becomes weight plus mass times acceleration. So in this case, your, let's say, for example, let's say weight is 100 newtons. See, in case 1, the reading of the scale would have given you 100 newtons. But let's say, see if the weight is 100 newtons, that means the mass of the object is roughly 10 kilograms, right? So 10 times 9.8 is 98. So let's say just a little bit over 10. So we can just simplify here, say mass is 10 kilogram. See, then tension is equals to weight, which is 100 newtons, plus mass, which was roughly 10 kilograms, times acceleration. And let's give it this system acceleration of 2 meters per second square. Well, if I put here 2 meters per second square, you can see then the reading of the scale will be 100 newtons, then plus this 20 newtons, 10 times 20. So the reading will be 120 newtons. So it will be more than actual weight. So that's why sometimes we call this apparent weight, which is the weight of the fish appears to be greater than, before. Okay, so obviously the fish doesn't have more mass, right? Doesn't have actual more weight. It just appears to be because the scale will give you 120 newtons rather than 100 newtons. Let's look at case 3, which is what happens when the elevator, oh, not a person, but elevator, I don't need the person over there. So here's the fish, here's the weight, here's the tension, but now as it's moving, let's say up, right? So here's the velocity, the acceleration is down. That means negative acceleration with positive velocity means that, let's say, elevator is slowing down. Well, in that case, what I have here is the same T minus W, that's my net force, because those only 2 vertical forces, equals mass times, but now I have mass times negative acceleration, right? Because acceleration is negative, which means that on the right side, I get negative mass times acceleration. Well, then tension will be moved away to the other side, becomes weight minus mass times acceleration. Well, we know that the weight is 100 newtons. Mass times acceleration, same thing, 10 kilograms times 2 meters per second squared, let's say. So minus 20 newtons. Well, tension this time is only 80 newtons. That means going from 100 newtons when the elevator is at rest, you get a tension increased when the elevator is speeding up upward, to tension decreased when the elevator is slowing down as it's moving upward. So as you can see, right, the weight of the fish changes depending on the acceleration of the system. And that's kind of what we can see that this is, again, what we call apparent weight, right, is the reading of the scales generally based on either normal force or the spring force or the tension, and it can change if the system itself is accelerating. All right, so let's look at another example here. So you have a car of mass M on an icy driveway, inclined at an angle theta. All right, so a couple of things from here. Icy driveway is indication that you should ignore the friction, okay? So whenever you are given directly the smooth surface or icy driveway and things like that, means that friction force can be ignored, okay? So that means in this particular case, we're gonna assume that car, as it's at the top of the incline and there is no friction, it will start speeding up down because of, the gravitational force pulling it down. All right, so then one thing we can do here is take the car, obviously, as object of our interest. So let me kind of draw this incline. So let's say here's the incline with angle theta. And let's say here's my car. I'm going to make it as a particle. All right, so one thing we do here is as the car is going down an incline, I want to make sure that that motion is one-dimensional. So what we do here is we take our coordinate system and tilt it. So we tilt our coordinate system so that my x-axis, right, is parallel to the surface and my y-axis is perpendicular to the surface. Let's try to get a straight line. So this is y-axis and this is x-axis. Because you can see, right, as my car then, as the car will be sliding down, it's only going along the x-axis, that's it. I can easily change my coordinate system, right? Basically tilting it like that, right? And, making the motion as one-dimensional and greatly simplifying my calculation. Let's look at the forces acting on the car. Well, we know that the car is on the surface. That means there is a normal force. So here's the normal force. Well, there's also Earth, right? As an agent, exerts gravity. And gravity, remember, pay attention to the normal force, which is not up this time, but perpendicular to the surface. So sort of like, let's say it's still in a positive y direction, but it's not straight up. Gravity always going to be then straight down no matter what. So here's my gravity. Here's the weight. Okay. And the angle that gravity makes with the negative y-axis over here happen to be the same theta as the incline angle. It's always the case. That means that's my free body diagram. Now what I have here is, you can see if I take that and break down weight into components, so then what I will have here is this. So this is the y component of weight along the y-axis, and this is the x component of weight along the x-axis. What you can see here is y component is balanced by the normal force, but x component has nothing to cancel, right? That means this wx component, or the x component of w, is going to be responsible for speeding up the car down the incline. All right, so let's do, remember, step 1. Step 2 is the force table. Here's my force table. These are my forces. X component, y component. So I have weight and I have normal force. There's no friction. Those are the only two forces right now I have. Here's net force. Now weight, looking at that free body diagram, you can see that X component, which is this guy, right? See if I can move this guy right here. Remember, I can move that over here, right? So as I move this weight here, you can see the triangle tells me that weight, the X component of the weight, is the opposite to that angle theta, which means the X component is given in terms of, weight. So